let's check out it. In this video, I'm going to be talking about state space realizations of transfer functions. And so in previous video, we saw that if we have a state space equation, so we've been dealing with things that look like this, and I'll stick with LTI systems, so where A, B, C, and D matrices, these are not varying as functions of time. So we saw that if you have something like this, and X is an n by 1 thing, and A is an n by n matrix, U is a p by 1 vector, so B it must be an n by p matrix, and then we're going to have some vector of outputs, let's say that's q by 1, and that's going to equal some C matrix times our state vector, and C must be q by n, to get the dimensions right, plus D times our U vector, and so D must be q by p. So we saw previously that if we have a state space formulation like this, we can always turn this into a transfer function matrix, where our transfer function matrix G of S will look like C times Si minus A inverse B plus D, where this G is our mapping from our outputs to our inputs. So basically we have that Y of S is equal to G of S times U of S. And in this case, so U is a p by 1 thing, and Y is a q by 1 thing. So G of S is a transfer function matrix that's full of a bunch q by p scalar transfer function. So each of the scalar transfer functions is a single input, single output transfer function that maps one of our inputs to one of our outputs, and it's a big matrix of these. So it's easy if you start with a state space formulation to compute the transfer function, and this is how you do it. You just plug it right in here. So the question is, what if you're given a transfer function? So what if I were to give you this G of S, and when I say transfer function, I mean transfer function matrix? Could you take this G of S and go back and figure out what A, B, C, and D are? And that's what this video is about. And the short answer to that is maybe. Maybe you can and maybe you can't. There are some transfer functions that there is no state space formulation for, and we'll talk about which kind of transfer functions those are. And if there is a state space formulation, it's not unique, and you can compute it different ways. And so what we'll talk about is a couple of different ways you can compute it, even though there's not really any one perfect way. So when we have this question of, I give you some G of S that's a q by p matrix of transfer functions, and can you compute an A, B, C, D matrix, that's the question of asking, is this transfer function matrix realizable? Basically, the way you can think of it is, if I give you a transfer function matrix, can you realize an A, B, C, and D state space formulation? And so if an A, B, C, D does exist, we say that this transfer function is realizable, and if it isn't, it's not realizable. And the thing that we have to remember is that if it is realizable, there are infinitely many realizations. And one of the easy ways to think about realizations is to think about similarity transformation. So that alone, will give us a bunch of different possible state space formulations that give us the same transfer function. And these are state space formulations that are similar to each other, based on the technique we've been talking about recently. But it even goes beyond that. It's not just a question of similarity. These realizations can even have different dimensions. So basically, this number n here isn't even fixed, and we'll see examples where that is sort of definitively shown to us that this n can be somewhat arbitrary. So that question of what is n, or what is the minimal number of n, is kind of an interesting question. So to answer this question up front, is this transfer function matrix G of S realizable? There's a theorem that says it's realizable if and only if it's a proper rational matrix. So it's realizable if and only if, and if you haven't seen this IFF notion, it means if and only if. And another way you can think about is a double arrow if and only if. So it means that I'm going to say something, it's realizable if and only if G of S is a proper rational matrix. And because if and only if is like a double arrow, if it's realizable, then it's a proper rational matrix, and if it's a proper rational matrix, then that means it's realizable. It goes both ways. There are synonyms of each other. So the question is, what does it mean to be a proper rational matrix? And what a proper rational matrix means is that each of the little sub-transfer functions are themselves proper rational transfer functions. So what does that mean? So remember that G of S is really full of a bunch of little single input, single output transfer functions. Okay, so let's remember that, and there's a bunch of these transfer functions. So let's focus on just one of these little transfer functions for a moment. So if I have a transfer function G of S, that's some ratio of polynomials. There's a numerator polynomial N of S over some denominator polynomial D of S. And when we say this is proper, what we say is, what's the definition of a proper transfer function? It means the order of N of S is less than or equal to the order of D of S. So, for example, if N of S looks like, I'll write an example, proper transfer function. Our D of S is like S squared plus 3S plus 2, and our N of S is S plus 7. So this is in order 1, and this is in order 2, so this is a proper transfer function. And in fact, this is actually a strictly proper transfer function. So, if I say strictly proper, that means that the order of N of S is less than the order of E of S. So I wrote a strictly proper transfer function because 1 is less than 2. A proper transfer function is okay for them to be the same as each other, so I can have S plus 7 over S plus 9. That's a proper transfer function because it's using this equality, but it's not strictly proper. So here's an example of a proper transfer function, and if we go back to our definition of what G of S is realizable, it's that G of S is a proper rational matrix, and to be a proper rational matrix, what that means is each of the little individual entries G of S are all proper. So as long as every single entry is proper, then G of S is proper, and it's realizable, meaning you can convert that transfer function into a state space formulation. But even if one of these little entries, G of S, just in one of these, here's your G transfer function matrix, and this one random entry right here is improper, meaning it's not proper or strictly proper. If even one of them is improper, then this is not a realizable transfer function, meaning there's no state space formulation for this. And these aren't mathematical anomalies. Real systems exist like this. So, for example, a PD controller. For those of you who've ever seen a proportional derivative controller in some other class, if we remember what a PD controller typically is it's got some sort of error signal coming in, and it's got some sort of motor voltage or something coming out the other side, and the PD controller typically looks like KD times S plus KP. So the transfer function of this, if I were to write the transfer function from error to voltage of PD controller, it looks like KDS plus KP, which you can think of as being over 1. So the order of this is 1, and the order of this is 0, because I basically have an S to the 0th power here. So this is an improper transfer function. So this tells us that a PE controller, while it has a very simple transfer function to write, has no state space formulation equivalent of it. So this can really happen to us But for many well-behaved systems, this won't happen. For those of you who have had class on PD controllers, you may remember that a PD controller is not itself a stabilizing controller, meaning it's not bounded out but stable. And that sort of lends itself to why it doesn't have a state space formulation. For those of you who have not seen that before, we'll talk about stability in the near future. So another thing that we're going to rely on is this ability to convert proper transfer functions to strictly proper transfer functions plus a constant. So I'm going to give an example. Let's say I have a transfer function, g of s, which is equal to 4s minus 10 over 2s plus 1. So this is proper because they're both order 1. It's not strictly proper. But I know I can convert this into a strictly proper transfer function plus a constant. And so the way I do that is I do long division. And the way I do that is I put the numerator like this, and I put the denominator like this, and I'm going to try and divide this into this. And you look at the leading term, and you say, how many times does 2s go into 4s? It goes in twice. Then you multiply the 2 by the 2s plus 1, and you get 4s plus 2, and then you subtract that whole thing off, and that always gives you a 0 here based on the method. And then minus 10 minus 2 is minus 12, and that's the remainder. So it goes in 2 times plus the remainder of minus 12. And so this g of s is actually equal to minus 12 over 2s plus 1, and then plus 2. And you can, by multiplying this 2 top and bottom by 2s plus 1, and adding the 2, you can get back to this and see that it is in fact true. So we turned a proper transfer function into a strictly proper transfer function plus a constant. And you can always do this by long division. So when we have some g of s, there's a big matrix of these things, we can do this term by term to each of the individual matrices, and we can factor out the strictly proper component. So now we have a big matrix of only strictly proper transfer functions, plus we can factor out all the constants, and we have this big matrix of constants. And your book calls that G infinity, but I'm not even going to bother doing that. I'm just going to call that D, because that's our D matrix. Because if you think about what G of S is doing, G of S, remember, is going to look something like C times Si minus A inverse B plus D. And this is the thing, this is the constant matrix. This is the matrix that directly maps, and remember this whole thing, we have our Y of S vector is equal to G of S, U of S. And so what D is it's the matrix that lets U go directly into Y. It doesn't have any history associated with it. I take U, I multiply by D, and that appears in Y instantaneously. Where this big matrix here is the thing that encapsulates the system's dynamics and how old inputs affect the current outputs. So the D matrix is just this big matrix of constants that's been factored out. So then the question becomes, how do I find my C, A, and B matrix? And that really becomes the problem of the realization. The D matrix is easy because it's just so straightforward. And so what we find is there are different methods that people have generated that they can sort of find an A, and A, B, and A, C. So not unique A, B, and C, but just possible A, B, and C that will work, that given a G will give us that. And your book goes through 2 examples that are very straightforward. There's example 4.6, which appears on page 103 of Chen, and there's example 4.7, which appears on page 105 of Chen. And those 2 examples are very well done, and I think they're more well done and clearer than I could repeat. So I just want to tell you, when you're looking at those examples, the conclusions that you should draw from them. In example 4.6, it shows a method that you basically compute the A, B, and C realization all at once, and in the end, the A matrix that you're given is a 6 by 6 matrix. So it's saying, I found a possible state space realization. It requires 6 states, so our x vector is a 6 by 1 vector, and that will work. That system will give you this transfer function g of s. In example 4.7, it shows an alternate method that's been developed, not necessarily better or worse, just different, and it finds another state space realization, and in that state space realization, it's A is a 4 by 4 matrix, and so that only required 4 states. So then that says, okay, well, should I have the one that requires 6 states or the one that requires 4 states? And it sort of is intuitively obvious that you'd want less states if you could get away with it. So choosing the A matrix that's 4 by 4 seems clearer. But I think the takeaway here is that this A, B, and C matrix isn't unique, and that somehow these 2 systems are not the same. They have different internal states that are evolving over time. But as far as you're concerned, the output Y, they're identical. And so I think where we want to leave at this point is this idea that different systems, fundamentally different systems with different states, can be evolving, and internally, all these states are varying in time, and yet what you see at the output Y is the same, even though inside these 2 systems are different. And this is one of the reasons why state space methods are so important and powerful compared to single input, single output transfer function methods that we learn in the classical controls class. Because we'll find that the stability of state space systems is actually much better described using state space formulations. And by only looking at the mapping from input to output that we do in transfer functions, we lose some of that information about what's going on internally. And so we'll see this in more detail in the future.